My guest today is Professor Lance Dixon, who's Professor of Particle Physics and Astrophysics at Stanford University and SLAC. He's interested in novel descriptions of how relativistic particles scattering and how those insights can be applied to a variety of problems. Welcome, Lance.
Thank you for having me on, Gill.
Yeah, thanks for doing this. So as I briefly described, Lance, I am sort of mathematically incompetent. But I find these topics extremely interesting. I go to sleep thinking about falling into a black hole most nights, and it has been very useful in getting to sleep. So we had some conversations, as the audience knows, about LIGO and Virgo, that is detecting gravitational waves. Advanced LIGO and Virgo now. We have ESA going out to doing LISA, taking it to the next level. And then we have LHC doing many particle physics experiments. Now, most people think of these things are distinctly different things. Black holes are big things, not necessarily big in diameter, but big in mass and momentum and so on. And the little things that we sort of squash together at LHC are really small things. So I want to start with the black holes. You have a quote here from Chandrasekhar. He says the black holes of nature are the most perfect macroscopic objects there are in the universe. So what do you mean? What did he mean by the most perfect macroscopic object?
I think he meant that they were very mathematically precise. There is a way of describing them. If the black hole is not spinning, we say that they solve a certain equation, which Einstein wrote down, his field equations of general relativity. And the solution to those equations, there was one found by Schwarzschild early in the 20th century, and it gives a very precise and very simple description of what space-time looks like everywhere near a black hole. And as far as we know, black holes obey these relations perfectly. And in the real world, they can sometimes have accretion disks of gas and dust around them, but sometimes they appear to be very naked or shorn of that dust, and then they should obey these equations. And we've seen examples of that with the LIGO detectors, at least seeing the gravitational waves when two black holes coalesce. And so far, it seems to be described by Einstein's equations as well.
Yeah, so in some sense, it's sort of counterintuitive for non-physicists, but in some sense, it's a simple object. You can describe a black hole with potentially three parameters, right? Mass, spin, and potentially electric charge, but
Correct.
most of them don't have an electric charge. So it's almost like two variables. We don't have too many things that could be defined by two variables in the world.
It's an extremely simple playground, and so lots of theorists have studied black holes under those circumstances, and sometimes they've enlarged the theory to have, for example, extra electromagnetic charges, and then they can get even richer solutions that may not have to do with reality, but it's a great mathematical playground because it is so simple.
So mass and spin are sort of the big things, right, for a black hole, but some of them are not even spinning, I gather.
Yeah, I mean, we don't know that much about how much they're spinning. There are two ways we see black holes. One is through electromagnetic signals. There were a handful of these systems where there might have been an ordinary companion that was accreting matter down onto the black hole. And you could see X-rays from that. I don't actually know how much evidence there was for the spin of those. And now we see more black holes through the mergers that have been seen through gravitational waves, through LIGO-Virgo observations. And there, the spin can be constrained. It's not easy to measure it precisely, but there is evidence that some of them are spinning, and the others may be spinning too slowly to tell. It's not completely clear yet. We're going to learn a lot more about this over the next decade. The spin is also very important to learn how these systems of two black holes formed. So did they form because they were originally massive stars in the same system? Or were they isolated and they captured later through what we call three-body interactions in dense environments? Those two scenarios have different conclusions about which way the spins are pointing relative to the way the black holes were orbiting. And some of that can be diagnosed with future data.
Yeah, I mean, it's an amazing accomplishment. I was looking at the Event Horizon Telescope picture. As something that was theorized 100 years ago, we could ultimately take a picture of.
Yeah.
It's an incredible scientific and engineering accomplishment. But what we're looking at there is not necessarily the black hole, but stuff around the black hole, right?
That's correct. That was taken electromagnetically, so you need gas and dust to be radiating. Actually, in this case, it was taken by a collection of radio telescopes across the Earth. So they made a synthetic or artificial aperture of a radio telescope the size of the Earth in order to make the image. But they needed radio waves. I'm not entirely sure, but I think they're usually from synchrotron radiation of electrons that are spiraling around in some magnetic fields that may be in the disk.
So the picture that we got in the radio spectrum, does it prove everything that we thought of the black holes, or are there anything that came out of that sort of put some question marks?
As far as I know, there are no question marks raised by that image, but I haven't read all of the relevant papers, so
it sort of it sort of proves the standard model in some way, right? So whatever was expected, we saw. And then we have the LIGO and the Virgo experiments going on to detect the gravitational waves of neutron stars or black holes merging. So this is the beauty of, I was talking to somebody else the other day that the beauty of the LIGO and Virgo is that it's on Earth. James Webb is going to L2. And that's a long distance away from us. If something happens, we can go out there. But here in LIGO and Virgo, we can actually look at things, right, with gravitational waves.
That's right.
So what do we have so far from LIGO and Virgo? I know there are advanced versions of both of these things operating now.
So let me just mention that radio image was actually of a supermassive black hole. So that's at the center of a large galaxy, and it has a mass of millions or maybe probably billions of solar masses.
That's the Andromeda.
Or maybe or M87. I think it might be M87. It's they also have plans to image the black hole at the center of our galaxy, which is a very large one too. But in contrast, the black holes that were seen have been seen by LIGO and Virgo are much smaller. They're of order 10 to 100 solar masses, roughly, most of the events. And there's a reason for that, and it has to do with the characteristic frequency with which things can orbit each other before they sort of touch and coalesce. If you have very big black holes, like these supermassive ones, they orbit very slowly. And there will be gravitational radiation from them too, but it will be at a very low frequency. And Earthbound gravitational wave detectors like LIGO and Virgo, they do their best to isolate themselves from seismic noise. But seismic noise is very strong at low frequencies. And so they can't go below about 10 hertz. And so these black holes have been radiating, the ones they see have been radiating for a long time, gravitational waves, but they've been at too low a frequency to be observed on Earth. So you just have to wait until they're close to the very end when they radiate so much that they spiral in and coalesce. And just in the last few cycles can you see them with LIGO. The neutron stars are even lighter. They're typically about 1 solar mass, and so things happen faster. And that means that they're spinning around fast enough for the gravitational wave to be visible for a few minutes, whereas it's less than a second for the black holes that LIGO's seen. When we have a space-based gravitational wave detector like LISA, which may also go out around the L2 point that you mentioned for Webb, I think that's the plan, then that detector will be able to see extremely slow period gravitational waves, and it will see these supermassive black hole coalescences too.
Yeah, so the supermassive black holes we have at the center of galaxies, like the Milky Way, M81, M87, they're already supermassive. So presumably they merged with a lot of stuff in the past. So do we have supermassive black holes? Do we expect supermassive black holes to merge in the current regime?
If there's a merger of two galaxies, there may be a point at which the supermassive black holes merge.
Right.
Probably more often you will see supermassive black holes eating stellar-sized objects, whether they're stars or black holes. Those will also radiate gravitational waves. It'll be a much more asymmetric system with a million mass thing eating a few solar mass thing. So it'll be a different kind of radiation, but the signal should still be visible.
So if two galaxies are merging, though, it should show up in the visible spectrum somewhere, right?
Yeah, there's I mean, I think there will be, shocks because the galaxies have gas in them and the gases are approaching. But, I think there are many galaxy mergers around there. And that is the kind of thing that takes millions of years. Whereas the final coalescence, when the two supermassive black holes get close to each other and radiate and then coalesce, that final stage would be much shorter than the millions or billions of years for the full galaxy merger.
So is LIGO and Virgo sort of fine-tuned to find neutron stars and lower mass black holes merging?
Yeah, that's correct. They have a certain window of frequency that they can see gravitational waves in. And the bottom of it, the lowest frequency is about 10 hertz or 10 cycles per second. And it's kind of in the audio band. It goes up through hundreds of hertz to about 1,000 hertz. They have other noise limitations. And so they don't see much past there. But that still gives them two decades in frequency. And that happens to be quite well tuned to these stellar mass coalescences.
Yeah, it's in the audio band. I remember hearing something that you can actually hear them merging.
Yeah, you should splice in an audio version of a LIGO chirp. It's quite amusing to hear.
It's an amazing thing. So I want to go to LHC now. So LHC is sort of on the other end of the spectrum. We are essentially smashing protons together and trying to figure out what comes out of it. Is that the way to think about it?
Yeah, particle physicists love smashing things together. And the general idea is that we can make new things when we smash particles together. And at the Large Hadron Collider, a particle was made that was never seen before anywhere else, and that was the Higgs boson. And so it has a mass about 140 times the mass of the proton. And but there was plenty of energy to make that, because the protons, which is what the beams being collided at the LHC are made out of. So you have collisions of proton on proton, but each proton has been accelerated to such a high energy that compared to its rest mass, it's about 7,000, more than that, times the mass of the proton. So that energy is available. In principle, you could make like 14,000 protons out of that, but that doesn't happen. But you can make elementary particles that weigh 1,000 times the mass of the proton if they're there. Now, the ones that are made in abundance is a lot of very heavy particles, some of which we've seen before. For example, the heaviest elementary particle we know is the top quark. And the top quark weighs 180 times the mass of the proton. And you make millions of them. The Higgs boson is harder to produce. It's lighter than the top quark, but it's quite a bit harder to make. So you don't make as many of them. In fact, the way you make the Higgs boson is actually by making virtual top quark and anti-top quark pair that then fuses into the Higgs. And this is a very strange way to make it, but the Higgs boson, it likes to talk to to particles that weigh a lot. But the proton is made out of particles that don't weigh very much. And so what actually happens to produce most of the Higgs bosons is that the particles we call gluons, they're called gluons because they glue quarks together inside the proton. And the proton itself contains these gluons as particles. One gluon from each proton comes together and they meet. And for an instant, they make a top quark and an anti-top quark, but not a real one, a sort of virtual one. In quantum mechanics, we have these virtual pairs all the time. And then the top and anti-top, because they're so heavy, they talk to the Higgs boson very efficiently. So this is how most of the Higgs bosons are made at the Large Hadron Collider, through this kind of a process called gluon fusion.
Gluon fusion. So I want to dig a little deeper into sort of the fundamental aspects of this. So if I understand this correctly, Lance, so you have, is it 2 up quarks and 1 down quark inside a proton?
Yeah, that's what we call the valence quarks. And so they sort of carry the quantum numbers of the proton. For example, if you add up the electric charge of the quarks, that's the up quarks have been determined to have charge 2/3 of that of the proton, and the down quarks minus 1/3. So you can add up 2 times 2/3 for the 2 up quarks, and then subtract off 1/3 for the down quark, and you get 1, which is the right answer. That's an example of what we call quarks that are valence, that they carry the quantum numbers of the proton. But then there are also these virtual gluons, or gluons and quark anti-quarks fluctuating around, and those can also participate in these collisions that I was talking about.
So I don't know if I understand this correctly. So there is sort of a sea of virtual quarks inside the proton, in addition to the valence quarks that sort of gives it a positive 1 charge.
Right.
And then you have gluons that sort of bind them together. So it's sort of a complex thing inside the proton.
Yeah.
It's an incredible thing.
Yeah, Richard Feynman once described proton-proton collisions as trying to collide a pair of Swiss watches together to figure out how they worked. But sometimes you do what you can. It's possible to accelerate protons to much higher energies than simpler particles at the moment. Simpler particles, the simplest stable particle is the electron. And we can make electron accelerators, but it's hard to store them and bend them in a circle at very high energies, because the electron is so light, it tends to radiate. electromagnetic radiation, not gravitational radiation, but electromagnetic radiation, and takes up too much power. So the same machine, the same ring where the Large Hadron Collider is now, previously it held the highest energy electron-positron collider. But that energy was much, much smaller than the Large Hadron Collider has. It was only a few hundred proton masses instead of 14,000. And that's because of this problem with the electrons radiating when you try to store them in a circle. People would like to build a linear collider with electrons and positrons.
Yeah, so protons, unfortunately, is going to be the thing that we're going to smash for a while for a variety of reasons. You need the electric charge to accelerate them, right? You cannot take a neutron.
Yeah, we don't know how to accelerate neutral particles very effectively, like a neutron. Also, a neutron is no simpler than a proton, so it wouldn't really help. So the particles that people have discussed accelerating, I mean, the only ones that have really been done so far are electrons and protons. You can imagine accelerating muons, and muons have been stored in storage rings at low energies, but they decay. When they're sitting at rest, they only last about a microsecond. So you have to act fast with muons.
So when the protons come apart, you have, as you said, virtual quarks in it, you have gluons in it. So things sort of break apart. So we found the Higgs boson in the, let's say, experiment. You said it's 150 times the mass of a proton?
Yeah, we usually use this unit called a giga-electron volt, and the proton is a little less than that. And in that unit, it's 125 of these giga-electron volts, or GeV.
So I don't understand this at all, Lance, but so my understanding is that Higgs boson essentially is sort of the mediator of gravity, or sorry, mediator of mass.
That's right. Not gravity. It doesn't directly have anything to do with the gravitational force. But we have a mass which is an inertial mass and how things accelerate without having to talk about gravity. And the Higgs boson is understood. There's a framework, the particle physics standard model, in which the Higgs boson, first of all, I should say that in quantum mechanics, anytime you have a particle, there's also a field. Well, I should say in quantum field theory. So like in electromagnetism, the particles of electromagnetism are the photons, and the field is the electromagnetic field. In the case of LIGO, it is producing gravitational waves, but those waves are the classical cousins of what we particle physicists would call the graviton. But also, we think that the Higgs boson, the particle, is associated with something called the Higgs field. And furthermore, this Higgs field, we think that it has a sort of non-zero value everywhere in space-time. And this crazy field talks to particles and endows them with mass, so that particles that otherwise would have been massless feel this field, and they get mass this way. And we can make predictions based on that for the relation between the masses of the forces that the carriers of the weak force, which we call the W bosons and the Z, and there's some successful predictions from that.
So how does the Higgs boson mass mediation interact with the graviton's gravity? Gravity mediation. What's the connection there?
Well, I would say that the Higgs boson gives particles mass, and gravity interacts, it feels anything with mass. But more than that, it feels anything with energy. So if you accelerate a particle to make it very relativistic, even if its rest mass is very small, the gravitational force will see that energy and momentum. So it sees the energy even if the particle mass is negligible. But most of the time we see particles that aren't moving very fast. And then most of their energy is their mass times the speed of light squared through E equals mc squared. So most of the time we see gravity, responding to where mass is or where matter is.
So graviton is sort of E plus mc squared. It's looking at the total content of energy.
Yeah, it's looking at E, the total E. So oftentimes you think of mc squared as the rest mass, and then the kinetic energy, which people at low energies goes like the velocity squared. The graviton would couple to all of that. When we talk relativistically, we call something E, which is the total energy. It includes mc squared, and it also includes contributions from the velocity.
We have no evidence for graviton yet, right, as a particle?
That's right. We only see gravitational waves in a regime where they are very classical. But most theorists think that, yeah, they're really just a collection of particles, like in any other quantum mechanical description. But to tell you the truth, we don't have, any strong experimental evidence that gravity plays with quantum mechanics. We all just kind of believe it because we don't know any other way to make something that is quantum mechanically consistent, unless all waves or fields are also can be interpreted as collections of particles.
Yeah, without knowing anything about it, it appears as two directions. You can take everything that we know quantum mechanically and try to extrapolate that to gravity, or you can take gravity and try to interpolate into everything else. The latter direction appears impossible.
Yeah.
So it looks like there's only one direction.
Quantum mechanics has proven to be a very difficult framework to modify. And people say that gravity is inconsistent with quantum mechanics often, but that's not really true. What is true is that if you try to assemble a theory of gravity and quantum mechanics, it looks like it's not going to really predict anything new. It becomes non-predictive. And what that means is that you try to calculate quantum corrections to processes involving gravity, and you encounter divergences that you have to make sense of. Now, to tell you the truth, even in electromagnetism, when you try to treat it fully relativistically and quantum mechanically, you encounter divergences. But these were encountered in like 1947, 48, and people understood how to deal with them, and they understand the framework even better now. It's a procedure called renormalization, where you have to redefine what you mean as the charges and how big the fields are. But after you do that, you get completely finite predictions out. And so people can calculate things like the anomalous magnetic moment of the electron to like parts per billion accuracy. And it agrees with the experiment. So this procedure that's part of it is called renormalization, and it's extremely successful. The problem with gravity is that the divergences can't be renormalized away. So we call that theory non-renormalizable. So it looks like you have to introduce a new parameter every time you go to higher accuracy. And because of all these new parameters, you don't get further predictions out. So that's sort of the general feeling about what we call quantum gravity when we base it just on particles and fields. Now, there's another area which I worked on in my youth called string theory.
Yeah.
And string theory avoids these divergences. It has a natural way to make everything finite. And so conceptually, it's a very, very elegant framework for describing quantum mechanics and gravity. And the graviton comes out sort of automatically in string theory.
Yeah, so the very little I know about string theory, Lance, it's so mathematically elegant, but we cannot really prove anything yet, at least. right? So
Yeah,
uh,
the most likely scale at which you would start to see particles not being particles, but being little loops of string would be at this scale we call the Planck scale. And that's also the scale where quantum gravity would become strong instead of being very, very weak, like we think it is at accessible accelerator energies. So that scale is some 10 to the 16 orders of magnitude beyond the LHC. So we can't reach that scale directly. So if we want to try to test string theory, it will have to be through indirect tests, possibly through how it makes predictions about the very early universe, things like inflation, whether there are B modes that many people are looking for. But it's not completely clear if those tests are, how conclusive they are. You could also try to predict some of the properties of the standard model of particle physics. It has 17 or 18 parameters in it, and we don't understand where they come from. Maybe the right theory of everything would predict them all, but so far it's been a challenge.
do you think, so I mean, we have a big problem with the standard model itself. I mean, we're still struggling with dark energy and dark matter,
Yeah.
which is 95% of the universe. Do you think the string theory direction could resolve some of those issues?
Possibly. I, I kind of think, well, I think that dark matter is a more accessible problem than, well, I'll tell you, I think dark energy may just be what Einstein thought his greatest mistake was, come back to haunt him, which is a cosmological constant or a constant vacuum energy. If it's just one parameter like that, it's going to be very hard to prove that you have the right theory of it because it's just predicting one thing. Whereas dark matter, there's a lot more phenomena associated with it. It should be affecting many properties cosmologically, and we have a chance to determine the particle nature of it if it is a particle. But we also have a lot of parameter space to explore, so it's a difficult quest.
Yeah, I mean, we're going a little bit away from your paper, but
Sure.
so I've seen some not data, but I've seen some hypotheses. There's a gravity is an effect on our universe by an alternative or adjacent universe. So that is why it is really weak. Um, what is your perspective on that?
Well, I'm not certain I know what you're referring to. So let me make a guess, which is that so actually in string theory, it's a natural context for a concept which is called extra dimensions. And the idea is that we have three infinite spatial dimensions, but it's also possible to have a dimension that curls up on itself like a circle. And so there could be a fourth spatial dimension or more, which are curled up into little circles. And then we have to ask, how big are those circles? So there's a characteristic length, the Planck length, which is related to this Planck mass I mentioned before. And the simplest idea for how string theory works, first of all, string theory would sort of prefer there to be 9 spatial dimensions and not 3. So we have to get rid of 6 of them. So we curl them up into 6 little circles. And the prevailing wisdom was that those circles were about at the Planck length. But suppose maybe one of them was much bigger. Then in some sense, gravity would sort of see that dimension and spread out more through that dimension and get weaker compared to other forces. So I think this idea of curling up dimensions and making them much bigger than this naive Planck scale, but still sub-millimeter, still not that big, that has been explored to try to explain the weakness of gravity, and maybe also related to it, the weak interactions.
Right. So I want to go back to LIGO now. So we detected this, I guess, two black holes merging, and we have sort of a characteristic wave pattern coming out of it as they revolve around each other and ultimately merge and then go into a different mode. So, I mean, I don't know the engineering aspects of LIGO that deeply, but this should be happening quite often, right, in the universe?
Well, LIGO is detected on the order of dozens, maybe pushing 100 of these. The very interesting thing is that the signal does not fall off very fast with distance. It's a wave, and it only falls off at 1 over r, 1 over the radius. Whereas like the flux from a star falls off like 1 over r squared. So even though it's not very easy to detect these, once you've detected them at some level, if you can get your noise down by a factor of 3, then the volume of the universe that opens up to you goes like 3 cubed, like 27 times bigger. So you can actually see events extremely far away once you can start to see events at all.
Yeah, so you talk about scattering amplitudes here. I have no clue about them, Lance, but so we have this quantum chromodynamics that sort of dominates LHC. So can you put this in sort of simple ways? So what do you mean by amplitude here?
Yeah, so the rules of quantum mechanics are that everything is probabilities. They're at the microscopic level, you can't say that anything happens in a deterministic way. Instead, there are probabilities. And the way you compute the probabilities is by trying to solve, like Schrodinger's equation, a wave equation, and those solutions are typically complex numbers. And then you square them to get the probability. And we call that probability the cross section, but it's just a probability for a certain scattering to happen. And it's a real number, and it's obtained by squaring a complex number. And those complex numbers that underlie the probability, those are called amplitudes. So
The
yeah.
complex numbers underlying the probability. So we can compute a probability of something happening, but underlying that probability is a complex number.
Yeah, so and like in the there's a famous double slit diffraction experiment, right? Where you send light through 2 slits and you see a series of peaks and troughs.
Yeah.
And the intensities there, they're all positive numbers. But if you want to compute them, you have to work out a complex amplitude for the electromagnetic field and then square it. So that's an analog of what we do when we compute these scattering amplitudes. It's like, where do the photons go in the double slit experiment?
Yeah, I mean, what's really fascinating for me with understanding a lot about this, Lance, is that you could take a black hole scattering and then sort of equate that to the sort of LHC experiment.
Yeah, so this is where the real mystery comes, is that there's a secret relation between the interactions of the gravitational field that is involved in the black holes spiraling in. Those gravitational interactions are secretly very similar to the interactions of these gluons that hold the protons together. And the equality is most easily seen when you look at the sort of simplest kind of nonlinear thing that happens. And the simplest nonlinear thing that happens, we call it a 3-point scattering amplitude. So it's like 1 gluon in and 2 gluons out, or 1 graviton in and 2 gravitons out. And when we look at the formulas for those two cases, the graviton case is literally the square up to some constant of the gluon case. So we say, we have a slogan, which is gravity is the square of gauge theory, or gravity is the square of Yang-Mills theory. Yang and Mills were the pioneers who first wrote down the field equations for the gauge theory that includes quantum chromodynamics. Actually, the weak interactions are described as well by what we call a non-abelian gauge theory. So in some sense, all of the forces of the standard model, unless you count the Higgs as a force too, all of those forces are described by these gauge theories. And so it's very interesting that in some sense, gravity looks like the square of them. When we look at the spin being carried by these particles, the gauge particles carry a spin of 1 times Planck's constant, whereas the gravitons carry a spin of 2 times Planck's constant. So this squaring is literally 1 plus 1 equals 2. So when you say it that way, maybe it makes, it's just simple addition. But then the consequences are much richer when you go from this very simple 3-point case, 1 in and 2 out, to more complicated cases. But you can literally use these techniques to understand the higher order nonlinearities in the scattering of black holes.
It's a beautiful thing. I can hear God chuckle, Lance. She's saying these guys are getting to it now. These things are all connected together. So is this sort of the direction that you think we should be really? So black holes really is a nice experimental factory where we could test or actually virtually test a lot of things. We have the LHC where we can smash protons together. Do you think this is where we are heading? We are trying to, the grand unification theories that have been proposed from the 1970s have eluded us so far. Do you think we are getting closer in that respect?
Yeah, I mean, going back to the gravity side and LIGO, this gives us an arena where we can see very strong gravitational fields. Most of the tests of relativity that have been done around the solar system are in very weak fields. And so far, they're all consistent, but the fields are very, very weak compared to what you have with these black hole mergers. So one hope is that we see something strikingly different or a little different. And this idea of using this relation to get more precise predictions for the gravitational waveforms, perhaps at some point there will be some deviation that shows up where the waveform doesn't look like the predictions. We don't know. It's still a ways off. It might have to wait for Lisa to explore these other types of coalescences too, or for more advanced versions of ground-based observatories. On the collider side, we still have a big puzzle, which we didn't really talk about yet, which has to do with not just dark matter and dark energy, but there's another puzzle that particle physicists have, which is why the weak scale is the scale that it's at. It just, when you consider quantum corrections, quantum mechanics, and the Higgs boson, it tends to change the weak scale and make it at a higher energy than we observe it at. This is just a thought experiment, but there's a fine-tuning problem that we have. And many people expected newer particles to be seen beyond the Higgs, which was predicted in 1964, to appear at the Large Hadron Collider, and they haven't yet. So we're wondering why there aren't any particles there. So the LHC is going to keep colliding particles for another, 15 years, and it's going to collect a lot more data as a result of upgrades. So there's still things to watch for there. that might guide us towards the next layer of unification.
Do you think we're on the right path, though, Lance? I mean, I sometimes feel, we are playing some sort of Russian doll game. We find something, and then you open that up, you find something else in there. Uh, are we getting closer to some fundamental understanding? I mean, I don't know much about this. The problem with experiments is that we tend to find things we look for in experiments. I mean, that's a grand statement. You can correct me if you believe otherwise.
Yeah, it's not always true. Sometimes you find things that you weren't looking for. I mean, take, for example, dark energy. That was an observation of supernovas. And they were trying to measure the deceleration of the universe, which is what would always happen if you had only energy of matter and radiation in it. So it was a complete surprise that the sign was wrong. Not only did they not measure deceleration, they measured acceleration instead. And so that was completely different. And I think actually there are many examples of discoveries that are made because of an increase in sensitivity of detectors. If you can build an accelerator that gives you 10 times the collision at 10 times the energy, usually, quite often you discover something new, and it's not always what was predicted.
Yeah, I mean, they say universe has no obligation to explain how it works to us. But do you think there is something to the idea that a simpler idea is always better? It seems to me, without knowing a lot about it, we are going down a path of complexity. We're finding more particles, we are finding more fields, but we are not really going further in terms of fundamental understanding. Is there anything to that?
Well, most of the particles we found recently were ones that were predicted 40 to 50 years ago. So those were all part of a theory that was built up in the 70s, by the 70s. And so they're not adding any more complexity. They're actually filling in the pieces of the puzzle. Now, if you saw something new that went beyond the puzzle, you might say you were just adding particles, and it looks worse. But I think most particle physicists would say these new particles are a clue towards an eventual unification. There are other ways we might see unification in our lifetimes, which could be the discovery of proton decay. That was actually the first suggestion from what were called grand unified theories when they were developed in the 1970s. They aim to put the strong interactions, QCD, into the same framework as the electroweak interactions, electromagnetism and the weak interactions we briefly touched on. Those grand unified theories always predict proton decay. The early versions of them predicted it to happen quite quickly, and they were soon ruled out because experimentalists, once they realized there was a live possibility of protons decaying, started putting a lot of protons in the form of water into big mines, and they quickly determined that the proton wasn't decaying very fast. And then more modern versions of the theories predicted slower proton decay. And so maybe we have an opportunity to see something like that happening. There has been a detector in Japan called Super Kamiokande, which has the best limits on proton decay, and it's going to be upgraded to Hyper Kamiokande, which will observe more protons more quickly than before. So maybe we'll see something there.
What's your intuition? You think proton decay is something that we can detect in
I think at some level protons will decay. Whether it will really happen in a rate that Hyper Kamiokande can see, it's hard to say, because it's a very strong function of the mass of the responsible particles. it goes like the fourth power of the mass. So you make them twice as heavy, and the rate becomes 16 times slower. And if it was like just beyond detection, then 16 times slower may be beyond hyper-K, or it will take a while.
So nobody has to worry, at least for now, that their protons are going to decay into something.
Even if one decays in hyper-K, that is so many human bodies that the odds that one of yours decays is not a problem. And I don't even think you get a little bit of radiation when one decays, but it's not really there very much in the grand scheme of things.
So I want to conclude on your intuition on, again, grand unification, because you're sort of looking at LHC and the LIGO data, and you're saying in very big scales we get data, in very small scales we get data. They seem to sort of have common characteristics that we can study. So do you think there is a grand unification underlying principle that we haven't yet found, or is it just a pipe dream?
Well, I worked in string theory for a while, and I still think it's a very nice conceptual framework. And it is one that removes these infinities that I was mentioning in quantum gravity. And it very naturally has in it both gravitons and the particles that make up gauge theories, gluons and things like that. So I think it's a very great all-encompassing framework. The task is to go beyond that and make more concrete predictions and understand the limitations of the predictions too. And at the moment, it seems very difficult to do that. There seem to be huge numbers of ways of going from sort of 10-dimensional string theory down to the 4 dimensions we observe. Hundreds and thousands of different possibilities. Well, actually 10 to the few hundred thousand is the last number I heard. And with that many possibilities, we may need other clues to know which is the right way for string theory to possibly be relevant to the real world.
So I have an education question for you. You're at Stanford. I often wondered, young students coming into physics, is there any value in teaching them Newtonian mechanics anymore? I mean, shouldn't they be going to string theory on day one? I mean, or whatever it is. I mean, we can teach computers Newtonian mechanics really efficiently. I mean, we don't need humans doing Newtonian mechanics anymore. So is there something with education that we need to also change?
Well, you can still, I mean, a lot of the things in the subatomic world, you need to go beyond the classical mechanics of Newtonian mechanics. But the classical picture is often a very useful predecessor to understanding what you want to do in quantum mechanics. For example, you start by doing classical mechanics with Newton's forces and so on. But there's also another approach to it, which is variational, which is you find a function and you minimize it. And when you minimize it, it tells you where all the particles go in Newtonian mechanics. And that's called the action, or sometimes the Lagrangian. And that becomes a very useful way to think about quantum mechanics, which Feynman first developed, which was a sum over many paths. Instead of just finding the one with the least action, you take all the paths. And so this insight from classical mechanics is a great way to understand the more complicated world of quantum mechanics. So there are lots of things you can learn about it, even if the goal of just numerically predicting where things go can be done by a machine.
Would you change anything in the sort of the status quo educational content that, that could push us forward faster?
Yeah, that's a great question. I mostly teach short courses in very, specialized areas. I really think that for the more general approach, I think that the ability to solve problems numerically and also symbolically should be integrated into curricula sooner. There are some very nice packages out there for doing symbolic mathematics. Many of my colleagues use Mathematica. I use Maple. I don't know, but I think that either of those could be integrated more into undergraduate physics curriculum, and people could see and play around with things in a way they, don't do it when they're just solving things by hand. Of course, you also want them to learn how to do problems themselves too, but this could give them more intuition about how things work.
And in a world of cheap computing and cheap memory, they could do very, very interesting things right from day one if they want to.
Yeah, we push our clusters of computers to the limit of their random access memory to do things in Maple quite often.
Excellent. Yeah, this has been great, Lance. Thanks so much for spending time with me.
Sure thing. Thanks, Gill, for having me on.
Thank you.
Bye.
Bye.